Hello, and welcome to our lesson on understanding when to use different kinds of diagrams in probability. Today, we will explore some intriguing concepts that will enhance your understanding of visualizing probabilities and improve your analytical skills. In this lesson, we'll delve deeper into our existing knowledge and learn how to choose the correct type of diagram for specific probability problems. First, we will revisit some basic ideas and then expand our understanding by introducing new types of visual representations. Finally, we will run through various cases to apply this new knowledge effectively. So far, we've built a strong foundation by becoming familiar with probability notation, understanding how to write and interpret different probabilistic events, the addition law, visualizations of probabilities, using basic diagrams to represent probabilities, including sample space presentation, two-way tables, frequency trees, probability trees, and Venn diagrams. We can now explore when and how to use different types of diagrams, which is crucial for breaking down complex probability problems. To begin with, let's examine when to use Venn diagrams. Venn diagrams are especially useful for highlighting the overlap between different groups. When we have information about groups and their intersections, Venn diagrams give us a clear visual representation of how the groups interact with each other. For example, let's say we have a sample of 100 people. Out of these, 56 people regularly shop at Tesco, 21 regularly shop at Sainsbury's, and 30 shop at both Tesco and Sainsbury's. The rest shop at neither. To find the probability of someone shopping regularly at just Tesco, a Venn diagram is perfect. We start with two overlapping circles, one representing Tesco shoppers and the other Sainsbury's shoppers. Place the number 30 in the overlapping section for those who shop at both. For the Tesco circle, subtract the overlap from the total Tesco shoppers, which would be 56 minus 30, which equals to 26, and do the same for the Sainsbury's circle to get 30 minus 30, which equals to 0. So no one shops at Sainsbury's only in this instance. This leaves us with 26 people who shop only at Tesco. Since the total number of people is 100, the probability of shopping at just Tesco is 26 divided by 100, or 0.26. Now let's look at probability trees and their usefulness. These diagrams are particularly helpful for representing sequences of events and their probabilities, especially when events are dependent on one another. For instance, imagine we have a box containing 15 black balls and 15 white balls. If we draw a ball and do not replace it each time, and we do this 5 times, we want to find the probability of drawing 5 white balls. We can begin by drawing the first branch of our probability tree, showing the probability of drawing a white ball initially, which is 15 over 30. The next branch is split into 2 outcomes for the second draw. This time, the probability for a white ball becomes 14 over 29, since one white ball has already been taken out. We continue this branching for each subsequent event. By multiplying these probabilities together, we get the overall probability for the sequence of drawing 5 white balls. It's important to note this is a case without replacement, as the probabilities change with each draw. In contrast with replacement, the probabilities remain constant. Next are frequency tree diagrams. These diagrams help us categorize data and visualize how categories become more specific as we move down the tree. Consider a cooking class with 40 participants. They have 2 options for each course: starter, main, and dessert. If we want to find out how many people chose option 1 for all 3 courses, a frequency tree is suitable. Start with a branch for those who chose option 1 for the starter. Suppose it's 15 people. For the next branch, note how many of these chose option 1 for the main course. Say it's 10. Lastly, see how many of these 10 chose option 1 for dessert. Imagine it's 5. Thus, 5 out of 40 people chose option 1 for all 3 courses, giving us a probability of 5/40, or 0.125. Finally, we have tables or lists. Sometimes the most straightforward approach is the best. Tables or lists are excellent for laying out all potential outcomes, especially in scenarios where there's a finite number of possibilities. Take, for example, the problem of rolling 2 dice and summing the results to get a total of 9. A A two-way table is ideal here. We create rows for the outcomes of the first die and columns for the outcomes of the second die. By filling in all the potential sums and counting how many of them equal 9, we can then determine the probability. For instance, the pairs 3, 6, 4, 5, 5, 4, and 6, 3 all sum to 9. With a total of 36 possible outcomes, 6 sides on each die multiplied together, we find there are 4 outcomes out of 36 that total 9, giving a probability of 4/36 or 1/9. In today's lesson, we explored the use of various diagrams to visualize probabilities effectively. We started by revisiting the fundamental concepts of probability notation, combining probabilities and basic visual representations. Moving forward, we examined specific scenarios to determine the appropriate diagram to use. First, we discussed Venn diagrams, which are ideal for illustrating the overlap between different groups. We used an example involving shopping habits to demonstrate how Venn diagrams can help calculate the probability of exclusive events. Next, we looked at probability trees, which are particularly useful for representing sequences of dependent events. By using an example of drawing balls from a box without replacement, we highlighted the step-by-step branching process that helps in visualizing changing probabilities. We then covered frequency tree diagrams, which are effective for categorizing and specifying data as we progress through different stages. We applied this to a cooking class scenario to find the probability of participants choosing a specific option for all courses. Finally, we examined the use of tables or lists for scenarios with a finite number of outcomes. Using the example of rolling 2 dice and summing the results, we showed how a two-way table can be used to count outcomes and determine probabilities. By understanding when and how to use these diagrams, we can tackle complex probability problems with greater clarity and efficiency. This lesson has equipped us with the tools to choose the most suitable diagram for different probabilistic situations, enhancing our analytical skills in probability.